Hello and welcome to MMI 701, the online version of the course Multimedia Signal Processing. This week we're going to talk about discrete Fourier transform. Now, last week we discussed different ways to analyze continuous and discrete time signals. If you have discrete time aperiodic signals, we use the discrete time Fourier transform, which is given as in these two equations. The first one is discrete time Fourier transform, and the second one is this inverse discrete time Fourier transform. Now, these are perfect if you want to calculate say for instance the power of a signal at a certain frequency as the absolute value squared of x of omega, or if we know what frequency we would like to analyze, then the DTFT would be excellent. But if we don't know which frequency we would like to analyze, then that's a problem because we would have to sweep all frequencies. Similarly, computers are not good at symbolic integrals, so inverse discrete time Fourier transform poses a problem to solve. So then the question is, how do we deal with this integral? Now, the simplest way, if you may remember from first year calculus, is to just use smaller so let's say we have a function which looks like this. What we would do is choose small rectangular or trapezoidal areas and just calculate the total area underneath the curve. So that would give us the integral, right? So that is one way of getting this integral, which would say, let's say this is x and this is f this is fx. Then if you want to calculate the integral, let's say integral is f equals to from minus infinity to infinity fx dx, then we can just use what is called a numerical quadrature in this case and solve the equation as a discrete sum. Let's say for all k from minus infinity to infinity, f k delta x times delta x. So that is how we would deal with this integral. So the question is, can we do the same thing for the discrete time Fourier transform? So let us divide the interval between minus pi and pi, that is our fundamental interval, to n partitions, so that we can just express x of n as, we're going to use an approximately equal to sign because we indeed are getting an approximately equal expression. For k from 0 to n minus 1, we have divided the interval into n partitions, so we're using those n partitions. X 2 pi over n times k, so that is the function that we're taking the integral of, e to the power j 2 pi over n kn times the length of each dx, so 2 pi over n, which is going to give us 1 over n, k from 0 to n minus 1, x 2 pi over n k e to the power j 2 pi over n kn. So that is how we would proceed then, and we're going to use that approach to express the discrete Fourier transform and inverse discrete Fourier transform. So let's have a look. So let us define then delta omega equals to 2 pi over n. So we divided the whole thing into n. Then we end up with the DTFT and inverse DFT, discrete Fourier transform and inverse discrete Fourier transform IDFT. So that is how we would express one of the most fundamental transforms which allows us to deal with discrete time signals. So here the question that you should be asking is this: why doesn't DFT, the bounds of summation in DFT, go from minus infinity to infinity? Indeed, in the case of discrete time Fourier transform, DTFT, these bounds were minus infinity and infinity. And right now we're saying our bounds are n from 0 to n minus 1. That is, we're calculating only, we're using only n values of our signal. So how come? So let's have a look at why this is the case. So why are the limits of the sum n equals to 0 and n equals to n minus 1? So let's express the discrete time Fourier transform at a given frequency, 2 pi over n times k. That gives us the expression that you see here. So n from minus infinity to infinity xn e to the power minus j 2 pi over n kn. We just substituted 2 pi over n k for our frequency, omega. So far so good. But something, a little note perhaps to get this thing going. We know that this is periodic. And it's periodic with period n. That is good to know, because what we're going to do in a moment is to use that property as well. So let's express this by using multiple sums. So what do I mean by that? I mean something which would look like this. So there will be many terms plus n from minus n to minus 1 x of n e to the power minus j 2 pi over n kn. Then plus n from 0 to n minus 1 x of n e to the power minus j 2 pi over n kn plus all the rest. So can we do something better, perhaps? Can we, for instance, express this sum? So let me just make this a little bit bigger so that it's more visible, at least. Okay, so we would like to express this sum in a slightly different way. So how can we do that? Let's have a look. I'm just gonna change the line size to a slightly larger. Yeah, okay. So that's better, I guess. Okay, so let's go on. Yeah, so let's have a look. So that is equal to L from minus infinity to infinity. We have an infinite series anyway, we're not getting rid of it. But right now we're gonna express a secondary sum. So we have a double sum with limits from lowercase l times capital N, that is capital N is our period, and Ln plus n minus 1. So we have n samples again, and x of n e to the power minus j 2 pi over n kn. Okay, so that is completely legal what we did. We're just re-expressing it, so everything else checks out. Now let's substitute n equals, well, instead of n, let's put n minus ln. So that's going to give us something slightly different. That is L again from minus infinity to infinity. But this time n from 0 to n minus 1. And x of n minus ln e to the power minus j 2 pi over n kn. What else? Let's just switch the summation. So we have n from 0 to n minus 1 and L from minus infinity to infinity, x of n minus ln e to the power minus j 2 pi over n kn. So something which is quite important here is the identification of this part of the sum as being periodic with period n. Now I'm going to leave it to you to show because it's really simple. I'm not going to show it for you, but you can show that it's periodic. This part only, the first part of the second sum is periodic with period n. And we knew that the complex exponential is also periodic with period n, so we have a periodic function to start with. So now that brings us to an important definition. And that definition is the periodic extension of x of n. So the blue part, the part I indicated with blue, this L from minus infinity to infinity x of n minus ln is called the periodic extension of x of n. So we know that this function is periodic. Oh, okay, so let me just show it because it'll be easier to follow if I do show it. I'm not going to leave this to you then. So let's say, here, just as a little note, xp of n plus n, okay, so just one period shift, is equal to L from minus infinity to infinity x of n minus ln plus n, right? But because we're getting the sum for all L from minus infinity to infinity, that's going to be equal to the same thing, L from minus infinity to infinity x of n minus ln, which means xp of n. So we have a signal which is discrete time periodic. So then, from 2 weeks ago, which analysis can we use for discrete time periodic signals? For discrete time periodic signals, we can use the discrete time Fourier series expansion. Just as a reminder, let me just write it to you. So that is, we would like to express xp of n, which is periodic discrete time, in terms of its Fourier series coefficients, and we're using k Fourier series coefficients. C sub k, these are the Fourier series coefficients, e to the power j 2 pi over n kn. Okay, so this is the discrete time Fourier series. And we can also express, obviously, the Fourier series coefficients as C sub k is equal to 1 over n from 0 to n minus 1 xp of n e to the power minus j 2 pi over n kn. But what is this then? That is, from whatever we saw from a moment ago, that is the scaled version of the discrete Fourier transform. So that is equal to 1 over n x 2 pi over n k, right? Which means by using the periodic extension, we can define the inverse discrete Fourier transform of xp of n as 1 over n k from 0 to n minus 1 x of 2 pi over n k times e to the power j 2 pi over n kn. That's good. So periodic extension of x of n. So let's say the red rectangle you see here is x of n, which is our signal which we want to analyze, and its periodic extension is the periodic repetition is, well, that part repeated over and over basically. So you see 4 repetitions here. So this is the periodic extension. So just as a little note then, x of n is equal to xp of n for the whole time support of x of n for 0 less than or equal to n less than or equal to n minus 1. So all of these are samples. And if we have that kind of a situation, then we can obtain x of n from xp of n. So we just get a single period. Now, one thing is important, however, and that is we need to set n greater than L. So that is, we don't want aliasing. So we would like to form a the period of our periodic extension to be greater than or equal to the time support of the signal. Otherwise, we're going to have aliasing. So let's go back to our definition of discrete Fourier transform and inverse discrete Fourier transform, and let us define. So let me just write it here. Let us define W sub n as our basic building block, basically, e to the power minus j 2 pi over n. by this definition, we can express the inverse discrete Fourier transform and discrete Fourier transform in a slightly more compact way. The reason why, well, you don't need to use Wn, you can use anything else. This is just by convention, but it makes things a little bit easier to follow in the long run. So that is why we're using Wn, W sub n. So then the question is, we have the inverse discrete Fourier transform, right? So this is I dft, and we have the discrete Fourier transform dft. The question is, can we express these in matrix form? And the answer is yes. So let's say we're trying to obtain capital X of n. So this vector over here from lowercase x of n, this vector in here. So this is the time domain, so discrete time, and this is discrete frequency. Okay, so we would like to obtain capital X n from lowercase n. And the DFT matrix is given in here. So let's have a look. The first row is all ones, because it's W sub n to the power 0. The second row is Wn to the power 1, etc. So this each element is kn. So Wn to the power kn. So the first row is all ones, first column is all ones, and the second row is Wn squared, Wn to the power n minus 1, etc. And the last column is Wn to the power n minus 1, Wn to the power 2n minus 1, etc. Okay, so by using this matrix, it is possible to express the discrete Fourier transform and discrete inverse discrete Fourier transform in this format by using a matrix multiplication Wn times xn and Wn inverse times xn. So then the first expression is the discrete Fourier transform, and the second expression is the inverse discrete Fourier transform. Now, several properties which we would need to know about this matrix. First of all, it's orthogonal. It's not orthonormal, but it's orthogonal, and that is, if you multiply the conjugate of the matrix with the matrix itself, you end up with the identity matrix. And same goes for the inverse matrix then. That is also good to know, because then it becomes possible to simplify things quite a lot. Because if you want to express then the inverse discrete Fourier transform, this is my bold symbol, bold X. We can just use 1 over n, the transform matrix conjugate times the DFT vector n. So we don't even need to get the inverse of the matrix in that sense. Okay, so properties of the discrete Fourier transform. First of all, since we're dealing with a periodic extension of the signal, our signal is assumed periodic, which means the DFT will also be periodic. Second one is linearity. If you have signals x1 of n and x2 of n, and you combine them after multiplying them by alpha and beta, you have the same operation in the frequency domain. So it is linear. Time shift. So let's consider a signal which has a finite time support. And let's say it has a length L. L is 8 samples in this case. Let's say this is N, and this is X of N. Okay, so this is our signal. The discrete Fourier transform of this signal is the same as the discrete Fourier transform of its periodic extension. So that is the same as the DFT of xp of n. So this is the periodic extension. So we just repeat the signal over and over. Okay, it's just 4 periods. And in this case, for instance, L is equal to 8. So the signal is from non-zero, from 0 to L minus 1, which is equal to 7. Okay? So this is our signal. This is the periodic extension of our signal. So just to remember it once again, xp of n is equal to L from minus infinity to infinity x of n minus Ln. So in this case, we have chosen n as 8, which means it's repeating it over 8 samples. So that doesn't cause any aliasing. And let's define a time-shifted version of this. Let's call this xp prime of n equals to xp of n minus k, some delay, we are shifting it. And that is equal to, for all L from minus infinity to infinity, x of n minus k minus Ln. That is this signal here. So xp prime of n. So we have shifted our signal, in this case, by, I guess 4 samples, is it? Sorry, 2 samples. So we delayed it by 2 samples. Then we define the time-shifted version of x of n. So let's call this. And so let's define the time-shifted version of x of n as x prime of n is equal to xp prime of n in the period that we're interested in, so the fundamental period, and 0 otherwise. Okay, so this is then x prime of n. That is the shifted version of our signal. That shows that what we're essentially doing is a circular shift. So, or a modulo shift, if you like. So, if you want to give an example, I'm going to give the example right here. So let's say n is equal to 4 and k is equal to 2, so we are shifting by 2 samples. Then x prime of n is equal to x, we're going to have a modulo operation, n minus k modulo n. So for instance, x prime of 0 is equal to x modulo shift minus 2 modulo 4, that is x2. X prime of 1 is equal to x 1 minus 2, that is x modulo 4, that is x minus 1 modulo 4, and that is equal to x of 3. X prime of 2 is x 2 minus 2 modulo 4, that is x0. And finally, x prime 3 is equal to x modulo index 3 minus 2 modulo 4 x1, which shows that x prime 0 is x2, x prime 1 is x3, then it wraps around and it becomes x prime 2 is x0 and x prime 3 is x1. So that is how you carry out time shift if you're dealing with the periodic extension, namely you're dealing with discrete Fourier transforms. So symmetric properties of DFT. Let's say that we have a complex valued signal x of n and its discrete Fourier transform x of k. There's a little typo here. I think I forgot to change this to k, so this is k as well. Okay, so x of n is equal to xr of n plus jxi of n, and xk is equal to xr of k plus jxi of k. So as with our example last week, xr and xi are all real valued. And then, just like we did last week, let's express the real and imaginary parts of these expressions. So x r of k is equal to n from 0 to n minus 1 x real of n cosine 2 pi over n kn plus x imaginary of n sine 2 pi over n kn. Similarly for x I of k, we have minus n from 0 to n minus 1 x r of n sine 2 pi over n kn minus x imaginary of n cosine 2 pi over n kn. Okay, and the time domain signal x r of n is equal to 1 over n for all k from 0 to n minus 1. I have to squeeze it a little, I guess, so let me just take this. Okay, so I'm just going to write it underneath, okay, because I don't think it's going to fit here anyway. So let me just write it here. X r of n is equal to 1 over n k from 0 to n minus 1. The real part of the DFT, x r of k, cosine 2 pi over n kn minus xi of k sine 2 pi over n kn. And finally, the imaginary part is xi of n is equal to minus 1 over n k from 0 to n minus 1 xr k sine 2 pi over n kn plus xi of k cosine 2 pi over n k. Okay, so we haven't done anything yet. We have just shown the same properties as we would do, or we did actually, for DTFT. And let's define two properties: circular evenness, circular oddness, so symmetry of the signal. So I'm going to write that note in here. So note, that's a definition actually. So we define a signal as being circularly even if we have x of capital N minus n period minus n is equal to x of n. So shifting the signal by n equals the signal, and so that is circular even. And we have the circular odd signal, that is x of n minus n is equal to minus x of n. So that is circular odd. And yeah, we have to define obviously the values of n for which this holds, and these are for all n from 0 to n minus 1. Okay, so let's have a look. Let's say we have a real signal which is also circularly even. What kind of a discrete Fourier transform do we have then? So that's right. So let's write the DFT, and from 0 to n minus 1, x of n, wn, kn, so this is our DFT. That is equal to x0 plus x1 wn to the power k plus many other terms. Well, actually, without writing even those many other terms, you can just express I'm just going to write it again. Sorry about this. So let's write it again. x0 plus x1 wn to the power k. And let's have a look. We have another term on the other side of the signal, which is x of n minus 1, capital N minus 1. And we have wn k times n minus 1. But what is this? First of all, we have an interesting property here, which is not immediately visible, but we have wn to the power k n minus 1 is equal to wn kn wn minus k. Okay, and this term here is 1. That is equal to 1, which means this is equal to wn to the power minus k. And what else? So we know that x1 is equal to x of n minus 1. So these two terms then, if you look at the sum of these two terms, or we have many other terms as well, so that's going to be the same thing for all the rest. But what we have then is x0 plus x1 times 2 cosine 2 pi over n kn plus, well, in this case 2 pi k because n is 1, okay, plus x2 cosine 2x2 cosine 2 pi over n times k times 2, etc. So we have many other terms. That means we can express the DFT by using the samples of the signal as n from 0 to capital N minus 1 x of n cosine 2 pi over n kn. That means the imaginary part of the DFT is 0. The DFT is real valued. And similarly, we can express x of n as 1 over n from 0 to n minus 1 xk cosine 2 pi k n over n. Okay, that's because the imaginary part is 0. So this is what we end up with. Okay, so what happens then if we have real and circularly odd signal? Then I'm just going to write the result here and don't spend too much time on it. XRK is 0 and XK, the DFT, is minus J times n from 0 to n minus 1 x of n sine 2 pi k n over n, and then x of n is equal to J times, 1 over n k from 0 to n minus 1 xk sine 2 pi k over n and times j, because xk is purely imaginary, so we need to get rid of the imaginary unit as well. Okay, so since we have a periodic extension and we have circular shifts, convolution property of DTFT translates into DFT as circular convolution. That's slightly different. So if you have two signals, x1 of n and x2 of n, we can carry out circular convolution of these two signals, and that circular convolution corresponds to multiplication in the frequency domain. So there is another typo in here, sorry about this. So this is k and this is also k. Okay, so let's have a look. Let's say we have x1 of n and x2 of n, and we're looking at the convolution. So let's define x3 of m as the convolution of these two, x2 of n actually, not m, that is equal to n from 0 to n minus 1 x1 of n m, sorry about this, I'm taking this all back, this has got to be m, sorry, and n from 0 to n minus 1 x1 of n times x2 of, now we have a delay term, but that delay is circular, so x2 of m minus n modulo n. So that is circular convolution. And we represent circular convolution by that letter n just underneath it. So this is the circular convolution, and this corresponds to multiplication of two DFTs, x1 and x2. Now we're going to see in a minute that this is a very important property. In fact, our next presentation is going to be about filtering, linear filtering. So some properties, time reversal. If you have time reversal because of periodicity, we end up with DFT expressed as shifted version of the DFT itself. So x of n minus k periodically shifts as well. Circular time shift. If you shift your signal by L samples because of periodicity, that's going to correspond to multiplication in the frequency domain by a complex exponential. That's very similar, by the way, to what we had before with DTFT and all Fourier transforms, basically. If you have a complex conjugate, x conjugate of n, that corresponds to capital X conjugate minus k, but modulo n, so we have x conjugate of capital N minus k. Circular correlation by the convolution property, you can show that the circular convolution corresponds to circular correlation between two signals x and y correspond to x of k times y conjugate of k. And multiplication in time domain corresponds to circular convolution in frequency domain. So these are some properties.